All right, everybody, welcome back. We are talking about sampling, and now we're going to go over some sampling methods, some different ways that we can draw our sample from our population using our list of elements in that population that, again, is called a sampling frame, right? Now, there are two main categories of sampling methods. They're called probability sampling and non-probability sampling. Now, the technical distinction between the two is slightly different than this, but the easiest way to think about it, even though this is technically incorrect, please don't, write in and tell me how this is technically incorrect. But the easiest way to think about it is that in a probability sampling method, every member of our population's chances of being selected are the same. In a non-probability sampling method, every element's in the population's chances of being selected are not the same. Okay? So if we've got this huge population, whether it's registered voters in the state of Vermont, or students at a particular university, or prisoners in a certain prison, if everybody has the same chance of being selected, that is essentially a probability sampling method. If some people are more likely to be sampled than others, is a non-probability sample. Okay? And we'll talk more about when to use each as we're going over each individual sampling method. Now, for the probability sampling methods, this is not a complete list. This is just a partial list, but these are some of the more common ones. The kind of easiest to understand and probably most common is just simple random sampling. You take your elements in the population, you take your sampling frame, you find some random way to pick whatever number you need for your sample, right? So if I have a list of every registered voter in the state of Texas, and I want a sample of 1,200, I might number my sampling frame from 1 through however many millions there are, and then use like a random number table or a computer to generate random numbers or something to pick 1,200 of those millions of numbers randomly. And those 1,200, those are my sample, chosen completely randomly, right? If we're dealing with phone numbers, what we can do is what's called random digit dialing, right? So a computer program just dials random digits within a certain area code or area codes. And that is essentially the same thing as a simple random sample, just using a computer to generate random phone numbers instead of random numbers that you can use within your sampling frame, right? Now, one of the things that is done a lot with random sampling is what's called replacement, okay? So let's say I have a population of 100, and I'm going to draw some sample, right? The odds of the first person getting selected are 1 in 100, right? But I pick that person randomly, I pull them out of the population, and put them in my sample. But now the second person I draw randomly, their chances aren't 1 in 100, their chances are 1 in 99. But I select one of those 99, put them in my sample. Now the third one I select, their odds are 1 in 98, right? So everybody's odds of getting selected are changing as I select my sample. That can be problematic with statistics. So instead what we can do is what's called replacement sampling. We choose our first person, their odds are 1 in 100. We put them in the sample, but we leave them in the population. Now we randomly select a second person. Now the odds are still 1 in 100 for everybody getting selected. And we choose a second person and put them in our sample, but leave them in the population. Now we choose a third person, and their odds of getting selected are 1 in 100. But let's say we choose one of those first two again. What do? Well, we just put them in the sample twice. And we allow their answers, their data, to count twice. There's no reason we can't do that. And a lot of times that makes our end result more accurate than it would if we didn't use this replacement technique, where the first person has a 1 in 100 shot, second person has a 1 in 99, third has a 1 in 98, and on and on and on. It depends on kind of which of those kind of negatives you prefer. The changes in people, in the odds of people being selected if you don't use replacement, or using the same person's data 2 or even 3 or 4 times, depending on the size of your sample, if you do use that replacement sampling technique. Now, another way to do this is called a systematic random sample. Okay? So let's say, once again, that we have a target population of 100 people. And we get our sampling frame that lists all 100 people. And we want to draw a sample of 10 people. Okay? What we do is we take our total population size, in this case 100, and we divide it by the size of the sample we want. In this case, 10. And our result is 10. And we're going to use that as our sampling interval. Okay? So now what we do is we generate a random number between 1 and 10. Let's say we get a 3. So that means number 3 on our list of 100 people, you're in our sample. And then we just add our sampling interval onto that. So 3 plus 10, our sampling interval, is 13. So number 13, you're in our sample. Number 23, you're in our sample. Number 33, you're in our sample. And that way, we get our sample size of 10 people. We've only had to generate one random number. And because we've calculated out exactly how many people we need to skip to get the exact sample size we want with the population size we want, we've generated that one random number. Now we go 13, 23, 33, 43, 53, 63, all the way down. We've got our sample. It's a randomly selected sample. As long as our sampling frame, our list of elements in our population, doesn't have any periodicity. Right? Periodicity means it's arranged in some way. That means if we do every X number of people, it might bias our sample, right? So let's say our sampling frame lists out all of the elements in our population as man, woman, man, woman, man, woman, man, woman, and it alternates gender like that. Well, in our case, we've got 3, 13, 33. Those are all odd numbers. And thus we would get an entire sample of only one gender, right? So if we're going to use this systematic random sampling method, we have to make sure that there is no periodicity in our sampling frame. If that is arranged in some way that messes with our sample, this systematic random sampling method can introduce a bias in our sample. Okay? So maybe it's, students at a university, but they're listed by year of, like, what class year they are, freshman, sophomore, junior, senior, right? Or maybe it's people in the sampling frame, they're listed by age, or some other method in which if we do it using this systematic sampling technique, we're going to be biasing our ultimate sample in some way that we don't want to, right? But if you have a sampling frame that is just kind of completely randomly listed, or listed in such a way that it's not going to introduce any kind of periodicity, you can use this technique. It's super simple, super easy, makes a much better, much easier, nice probability sample at the end of it. Third one we're going to talk about is stratified random sampling. Okay? Now, with stratified random sampling, usually what this has done is to guarantee some either equal representation or much larger representation of some population group, right? So let's say we want to sample prisoners, but we really want an equal number of men and women in our sample for some reason. Something based on our research question, something based on our research design means we really want an equal number of men and women. If we just pull out 500 random prisoners from a list of every prisoner in the state or in the country, the vast majority of those are going to be men. We're going to get a fairly small group of female prisoners in a group of 500 randomly drawn from prisons. So what we might do is do a stratified random sample that means instead of drawing 500 randomly, we're going to draw 250 men and 250 women, and then within each of those categories use, say, a simple random sample or a systematic random sample or something, right? And then we're going to have our ultimate sample of 500, but we're guaranteeing that there's 250 men and 250 women. And in that example, that was a disproportionate example. We are disproportionately sampling women compared to men. The odds of a woman getting selected for our sample is much higher than the odds for a man getting selected for our sample, just because we're drawing equal numbers, but the female prison population is so much smaller. But now let's say we're drawing a sample of registered voters. Registered voters are close enough to 50-50 men and women, but we still might want to guarantee we have 50-50 men and women, so we're going to do a proportionate stratified random sample and draw 500 men and 500 women. Even though we probably would have gotten close to that if we had just done it completely randomly, we might need to guarantee that it's exactly half men and half women for some reason. And so we can do a proportionate stratified random sample. The last probability sampling method we're going to talk about is cluster sampling. And this is when we have some large complex operation. So let's say we want to know the opinions of criminal justice policy and a new gun control law for the entire United States. But we don't have a good sampling frame for the entire United States. And it would be really tough to go out there and find one. So what we might do is say, well, there's, 5,000 counties across the 50 states. Let's take a random selection of 200 of those counties. So we do a random sample of 200 counties out of the 5,000. Now within those 200 counties, let's do a random selection of 50 people from each of those counties. So we end up with our total sample of whatever 50 times 200 is, people to interview about this new law or new policy or whatever. But instead of having to find a sampling frame from 5,000 counties, we only have to find a sampling frame from 200 counties, which is way easier, right? So that kind of cluster sampling, that multi-stage sample, where you take our target population and then take a sample of subgroups and then take a sample of individual elements from within those subgroups, that's a cluster sample. Or you could do it even 3 stages. So target population, take a sample of subgroups, then take a sample of subgroups within those subgroups, then take a sample of the elements within those subgroups of the total population. Right? Now, non-probability sampling methods. This is where everybody's odds of getting selected to the sample is not equal in any way. Right? And the only real reason to use non-probability sampling methods is when you have to. Okay? Using non-probability sampling is never better than using some kind of probability sampling method. The only reason to use a non-probability sampling method is when you're forced by the situation to use it rather than some kind of probability sampling method, right? So One of the ways we can do a non-probability sampling method is what's called convenience sampling, sometimes known as availability sampling, right? And this is where just, look, I have this convenient set of people I can talk to, I'll just talk to them, right? So if I wasn't really worried in doing research, like for publication, for advancing science, I was just kind of, mildly curious about something for my own personal ends, and I wanted to know how the students at my university feel about something. I don't know. Do y'all still like Taylor Swift? Right? As a convenience sample, I might just use the students in the class I'm teaching. Right? Now, they are not really a good representative sample of all the students at the university. They're almost definitely going to be criminal justice majors. Depending on which class it is, they might all be freshmen or they might all be seniors. So they're not a good, nice representative sample of the entirety of the student body of my university. But again, I'm not planning to publish this. It's not a really huge deal if I'm off. I'm just kind of curious. So I might use a convenient sample of just the students sitting in my class that are right there, right? If I needed somebody to just test out a survey, not to actually gather data from it, just to see if, the wording is clear and make sure that my computer works to scan their answers and stuff, but then I'm just going to get rid of all the information that they give me, I might use a convenient sample just for that. And then use a probability sample when I actually give the survey and actually keep the data and do the analysis for it, right? Quota sampling is kind of similar. This is where I say, okay, I need 100 men and 100 women. So I'm going to stand on a street corner and ask everybody that passes by, hey, you want to take my survey? And once I get the answers from 100 men, I'm going to stop asking men and only going to ask women. Or if I get 100 women first, I'm going to stop asking women and only answer men until I've got 100 of both. Right? There's purposive or judgment sampling. This is where you kind of on purpose pick. So let's say I've got a group of 100 people that I want to draw a sample from. I might kind of say, well, I need one or two people who are kind of look like this, young, this level of education. So, you and you. And then, well, I need somebody who's a little older and has been working in the field of business for a while, so I'm going to pick you. And well, I haven't picked many Hispanic people yet, so I'm going to pick you. And so this is where you kind of purposefully draw out a sample, usually to make sure it's representative, but not always, just based on whatever kind of aspects that you need for your sample. You just kind of say, well, I'm going to pick that one out of the population, and I'm going to pick that one and that one. And you kind of create a sample based on your own kind of purposive judgment in what might make a good sample, right? And then the last one here is snowball sampling. And this is one that's actually used a lot in criminal justice for a non-probability sample, just because there is no good sampling frame for criminals who haven't really been caught or haven't been caught yet, right? So if you want to talk to, say, heroin users or computer criminals or something, but not ones who have been caught and either are serving time or have served time or something, you want to talk to current heroin users, current cyber criminals, not necessarily ones that have been caught before. You might use a snowball sample. And this is where you start off with either one or just a few members of this target population, and you say, hey, will you agree to participate in my research? And then you do the interview or the survey or whatever. You gather your data from that person. And when you're done gathering data from them, you say, hey, I really appreciate you participating in this research. Do you know any other members of your group, other heroin users, other cyber criminals, whatever, who might want to participate in this research? And you write down their names. And then you go to them and you say, hey, do you want to participate in this research? And if they say yes, you do the interview, do the survey, whatever. And you say, hey, are there any other people that are members of this group that that might participate in this research? And they give you some names, right? So in that way, it starts with one or a few people, And then based on who they know and who they send you to, it snowballs and grows bigger and bigger and bigger until you have whatever size sampling you need, right? That's nowhere near a random sample, so it's not a probability sample, but it can get you a pretty good size sample of people who are otherwise really, really difficult to reach, okay? Now, once we have our sample, whether it's a probability sample, non-probability sample, whatever, we have to kind of grade our sample. How well did we do kind of getting a good sample of our target population? Well, here's where the problems come in. There are two kinds of error. There's the systematic error and there's random error. Once again, random error is definitely going to be there. But the good news is we can tell you probabilistically how close to reality, how close to the actual target population our sample got, right? Depending on the size of our sample. So random sampling error is a problem, but at least it's a known and understood and easily gauged problem. The much more insidious problem is systematic sampling error. And this is where you have either knowingly or unknowingly done something in your sampling technique that has given you a different sample than you should have based on the population, right? So a great example here was back in, oh God, what was it? It would have been 1948 when Truman was running for re-election, right? And all the polls said his opponent was going to win. All the polls said his opponent was going to win. And that's why some newspapers on the morning after the election automatically ran newspaper headlines that the other guy had won. There's a famous photo of Harry Truman holding up a newspaper and smiling. It says, "Dewey defeats Truman," even though he had just won the election. Because all the polls that had predicted that Dewey was going to win were wrong. And it wasn't because of random sampling error. It was because of systematic sampling error. Those polls weren't sampling a good representative population of the voters. They were sampling richer voters. They were sampling the much more wealthy voters than the actual population of the United States. And the wealthy voters were much more likely to vote for Dewey than they were for Truman. So all the polls predicted a huge Dewey landslide because of that systematic sampling error by the pollsters that they didn't know about or didn't correct for. And that led to a completely inaccurate sample. Okay? So if you don't know that you're doing something wrong, if you don't know that some aspect of how you're drawing your sample or where you got your sampling frame from or whatever, if there's some aspect of that entire process that has introduced a real systematic bias into your sample, you don't know about that. You can't correct for it. The way you can at least measure that random sampling error, which is just through pure random chance, we did everything right. There was zero systematic sampling error. Our sample is going to be slightly different than our population. That random sampling error, again, is known, easy to kind of measure probabilistically. But if you don't do everything right and you introduce a systematic sampling error, that can be a really big problem. But once we've drawn our sample, what we can do is say, based on the size of the sample, based on a few other factors, we can draw up what's called the sampling distribution. And it takes the shape of a normal curve, right? Just like here in this image, in that distribution. And that represents kind of how much random sampling error we probably have. So our actual measured value is right there in the middle at the peak, right? The real value of the population is going to be somewhere under that curve, okay? So let's say we're talking about voting behavior in the state of, what's a big swing state? Pennsylvania. Voters in the state of Pennsylvania. We sampled 1,200 registered voters, asked them who they were going to vote for, and 52% said candidate A. So under that normal distribution, right there in the middle is going to be 52% for candidate A. The real value, assuming we didn't have any systematic sampling error, we have only random sampling error, the real value for what percentage of the vote candidate A is going to get is somewhere under that curve. And if you'll notice, the most likely places for a spot under that curve is right in close to where we measured at 52%. But there is a small chance that it's way over here to the right or left at, say 57% or 49% or something, right? It's most likely between, right there in the middle. So what we usually report, and if you look at political polling especially, but in really any kind of sampling, you're going to have what's called a confidence interval. And through convention, we report the 95% confidence interval. So basically what you say is, we have measured this thing at 52% in our example, but it could be, pick a number. And our confidence interval says we're 95% sure it's 52% plus or minus, say, 3%. So in this case, we'd have a confidence interval of 95% at 3 percentage points. We can get that confidence interval smaller with a larger sample size. So if we interview, say, 1,500 instead of 1,200, our sample size is going to get smaller. Now maybe we're at 2.5%. So we're 95% sure that the real value is that candidate A is going to get 52% of the vote plus or minus 2.5%. This could be 54.5 or 49.5, but somewhere between there. Now, the best way to shrink our confidence interval is through getting a larger sample. So a sample of 200 is going to have a really huge confidence interval. It's going to be like 7% or something. But a sample of 500 is going to have a much smaller confidence, that 95% confident it's between this and this. We do a sample of 800, we're going to be 95% confident it's between this and this. If we do 1,000, it's 1,200, The problem is there's diminishing returns. So the jump from 200 to 300 is going to shrink your confidence interval a lot. Then moving from 300 to 400 is going to shrink it, but not as much. And 400 to 500 is going to shrink it, but not as much. And moving from 1,100 to 1,200 is going to shrink it, but way less than the jump from 300 to 400, right? So every time we're increasing our sample size by the same amount, and every time our confidence interval is shrinking, but the amount of shrink per jump is getting smaller and smaller and smaller and smaller and smaller, to the point where once you get to a certain sample size, increasing your sample size by another given amount is really not going to decrease the sample size very much. It's going to decrease it some, but is it really worth it? Adding another 100 people or 200 people or 500 people is only going to shrink our confidence interval a tiny bit. Might as well save the time and money and just deal with the slightly larger confidence interval, right? The other way to shrink your confidence interval and get a more accurate, more representative sample is to have a more homogeneous population. The more everybody in our population is similar to each other, the easier we're going to have taking a sample and using that to make conclusions about the larger group, right? Now in the United States, that's pretty difficult because we are not a very homogeneous population. I don't care what state you're talking about. We are a hugely diverse population in race and gender and religion and political beliefs and all those other factors. We are a hugely diverse country. But if there's some other population you're talking about, maybe it's prisoners are slightly more homogenous than the U.S., but not really. But if we're looking at other countries, especially smaller countries, say South Korea or Uganda or, some smaller country, they're going to have a much more homogenous population than the United States. Still nowhere close to perfectly homogenous. There's still lots of variation in, again, race, religion, gender, political beliefs, all that stuff. But it might be more homogenous than, say, the entire United States. Okay? Now, one last thing I'm going to talk about, and that is some common errors when talking about this kind of samples and error and conclusions that we can draw from any of this data that we've collected from our sample. And that is, if you have individual level data, don't use that to necessarily make conclusions about groups of those people. And if you have group level data, don't use that to judge any individual members of those groups. Because if you have data about individuals, all you can really use that data for is to make conclusions about individuals. If you have data about groups, all you can really use that for is to judge data about those groups, right? And this is a relatively common problem. So we need to make sure if we've got individual data, we're only making conclusions about individuals. And if we have group data, we're only making kind of judgments and conclusions about groups. Okay? All right. That's the end of this section. Thank you so much for watching.